Saxon Algebra 2, Lesson 78. Welcome to the wonderful world of force vectors. Take a minute and just appreciate what a cool name that is. Force vectors. Oh, Micah, what'd you learn in math today? Oh, you know, just some force vectors. Abby's name dropping with her friends. Yeah, I studied some force vectors today. I can see it. Kyle wouldn't say anything because Kyle doesn't speak very much about math. At least not when I'm around. Maybe he talks about it endlessly with you guys. That's a very real possibility. I suspect that Kyle exhausts his conversational well of words with you guys so completely that isn't anything left over to talk to me. Okay, you're all quaking in your boots at the sight of this picture because this looks really, really hard. And if you think too much about it, you'll freak yourself out. So don't think too much about it. Let me tell you what to think. In physics, there is a lot of work done to study forces and masses and velocity and acceleration, various different things. We are not studying those things, all right? And this is a problem that would show up in physics, and I'm going to explain it to you as simply as possible and then switch it over to how we deal with it as a math problem. This is a rope. This is a pulley. Imagine there's a piece of masking tape on the rope, like painter's tape, like blue, I want to say, right underneath the very center of that pulley that's marking a point on that rope that we care about. Don't ask me why. And this represents the direction and a force pulling on the rope this way. And then there's another direction and a force. This is the direction, this is the force, pulling on it this way. All right, so a tall dude with big muscles is pulling over here, and a shorter dude with smaller muscles is pulling over here. This one's stronger, and he's pulling higher. This one's not as strong, that's why his force is less, right? 70, 40, and he's pulling at a lower angle. The question is, if they both pull with that amount of strength at that direction, what's going to happen to that little piece of paint? Is it going to go this way? Or not, it's not paint, it's tape. Sorry, painter's tape. Is it going to go this way? Is it going to go that way? Okay, that's what we're trying to figure out, is where is it going to end up and how can we measure that? Now, here's the magic, and I'll just let you see it in the book. All we have to do is take, you notice that these are polar coordinates, right? There's the hypotenuse and there's the angle, right? That's what makes it a polar coordinate. We're just going to redraw them as triangles and add them, right? And get the resultant. And then we will turn that into a picture too, all right? So once we get our bearings with this wacky little diagram and an experiment that's contrived here, we turn it into triangles and we do it just like we've done everything else. So the only part that is new is looking at this picture and not passing out. Breathe. If anyone's hyperventilating right now, please fan them with a notebook and cool them down. So don't faint. Quickly draw the triangles, and then you're on solid ground, and nothing will be scary ever again. Okay, so that's what I'm doing right now. I'm taking that original picture, and I'm turning it into two triangles. And I remember this was the stronger guy and this was the weaker guy. This one was a 70 pull and this was a 40 pull. That doesn't really make sense to us because, like, how do you measure someone's muscles? We don't know, but guess what? We don't care because we're not taking physics right now. We're doing the math. Yay. This is 45 degrees. This is 30 degrees. As soon as I see those angles, I go, hot dog and hallelujah. We can do this using our, have we learned both of the triangles yet? No, we haven't, so never mind. We'll use our calculator still. All right, so what I want to do is I want to rewrite both of these in rectangular coordinates. So number one was draw triangles. And again, I just kind of lifted them, I didn't even kind of, you just lift them out of the picture. You don't have to interpret or do anything special. Just take that information and make triangles, right? Okay. draw triangles to convert to rectangular coordinates. I'm writing that uppercasey. And add. And then in this problem, it says, what is the resultant force? Never mind. I'm not going to do that. No, I'm just going to write translate to polar coordinates if needed. Okay, so what I'm going to do now is I'm going to give you a fairly detailed explanation of how we take polar coordinates and transfer them into rectangular. Micah, I hope you're wearing your aluminum foil helmet and your thinking cap. Are they the same? Probably. Because this is what we're going to do. Let's start with this one, okay? Now, here's our angle. We know that this is our adjacent side, this is our opposite side, and this is our hypotenuse, right? And in order, we can kind of imagine that these guys are in a, they're not perfectly lined up, but pretend they're in a grid, right? Cartesian coordinate system, if you will. We can imagine them in that. Just kind of extend this ever so slightly so it looks a little better, right? So what we want to do is we want to find this distance, because this will be the right distance. And we can see that since we're going this way from the origin, right? This is our y-axis or our up axis. This is our right axis. Since we're over here, we can see that this triangle, this is triangle A. Triangle A is going to have a negative right value, and it's going to have a positive up value, right? Because we're going up. Okay? So what we have to do is we have to figure out how far this distance is. Now we notice that the distance we want to measure is exactly equal to the adjacent side. Huh. Okay, let's just note this down. Sine, cosine, tangent. Oscar had a hold over Arthur. Still choking him. We know the angle and we know the hypotenuse. So if we want to find the length of this side, which will tell us our right measure, we can use adjacent, hypotenuse, and the degree measurement. Here's how we do it. We're going to say the cosine of 45 degrees equals A over H, and H equals 70. Okay? So we can use this. I'm going to just eliminate that now because I don't want that to confuse me. We have a value for H, so I plugged it in. So we can use this little formula to find out the length of that side, which is our negative right value, which is what we're looking for. So we're going to use cosine to help us get it. We know the cosine of 45 degrees equals the adjacent over the hypotenuse. The hypotenuse is 70. We've got 2 out of 3 of the holes filled, and we're ready to turn to our calculator. Now to solve this, we want to cross multiply. This number we always write in front. So I can see that side A is going to be equal to 70 times the cosine of 45 degrees. Now we turn to our calculator. We enter 45. Then we hit cosine. I think you need to hit equals after that. And then times 70. And what we will get is that the length of that side A, is 49.797. No, 49.497. Okay, so that is our minus right value. 49.497. That is the length of this. Now we need to do the same thing for this side because that's going to give us our up value, right? We measure it on the axis, but it's exactly the same as this side, right? Because that's even. So now we're going to do the same thing, except instead of using the adjacent side, we want the opposite side. So we're going to say that the sine of 45 degrees will equal the opposite over the hypotenuse, right, which is, again, 70. We'll do the same thing. We'll cross multiply. This will come up and we'll write it on the front side. So we'll say the opposite side is equal to 70 times the sine of 45 degrees. Sorry, that's getting squishy. And so the opposite, interestingly, also works out to the very same measure as the adjacent. Equals 49.497. What we just did was and this is all triangle A, by the way. That's all this side. What we just did was we took the degree measurement and the hypotenuse, and we used cosine and sine to get the right and the up values respectively. Now, John sometimes calls this like uppercase A and uppercase B. I guess he calls this one A and this one B. No, don't do that. Don't do that. That's confusing. Only refer to these sides as opposite and adjacent accordingly. Because once he throws the A and B in there, then now we've got other letters and it's confusing because what about these letters? No, 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 no. I only use this one just so that you could see this is the triangle I'm talking about. Then I'm going to do this triangle down here. But otherwise, I'm not using these letters to describe parts of the triangle. That's nutty. Okay, so I'm going to do the same thing here. From this angle, this is the adjacent, this is the hypotenuse, the opposite, and this is the hypotenuse, right? Now I'm going to do the same thing. First, I want to figure out, let's see, it's going to be a positive right and a positive up, right? Because I'm in the first quadrant here where everything's sunshiny and positive. Once you get the hang of this, you'll find that finding the measurement for the right, which is always what we do first, always involves the adjacent side, and adjacent is associated with cosine. So when you're trying to find the right coordinate, use cosine. Okay, so I'm going to do this same calculation, but I'm going to just shortcut it. So I know that the adjacent side will be equal to the hypotenuse times the cosine of the angle. I run that through my calculator. Again, put in the degrees first, then hit the regular cosine function, not the -1. We'll talk about that when we need it. The regular cosine function equals, if you need to, times 40, and you should get 34.64. We can put that right in here. And now to do the up measurement, right? It's the same as the opposite, even though we're not measuring it here. It's the same, right? That's going to be the same up coordinate. And it's the opposite side, so we know we want to use sine. So we say that the opposite side is equal to 40, the hypotenuse, times the sine of 30 degrees. Run that through your calculator, and you will get a value of 20. Okay? Again, do not use those letters that John uses. That's confusing. Always call your sides by their actual names, opposite, adjacent, and hypotenuse. Then when you're trying to connect them to the trig values, it'll be straightforward and easy. Okay, final step. We want to combine the two rectangular coordinates by adding them. Now, I've spread them out across the page. I'm not going to rewrite them, okay? That just That would be sad. So what I'm going to do is I'm going to take 49.497, put it in the calculator, hit minus. Then I'm going to add 34.64. As I'm doing that, I'm thinking, these are about 15 apart, and my answer should end up being around negative 15. What your calculator should tell you is that the answer is negative 14.86 to the right, plus, now let's look at these. We have to add these. Oh, this one's easy. We don't even need the calculator, right? Because this is just an even 20. We're adding our two up values, and we get 69.497. Okay. Fabulous, right? Is this the right answer? Yes, John rounded that. Oh, I forgot the U. Okay, so what we have done here is we have taken polar coordinates that we took from our picture with the rope and the pulleys that was confusing, but we don't even care about that. And we turned them into triangles and then did our usual thing that I explained in very methodical fashion, okay? And this is the right answer. Now, if you look in the book, you'll see John takes these rectangular coordinates and turns them back into polar coordinates. We're going to forego that step now, and we're going to do one more example, and I'm going to do it in that example because I want to make sure that this process is very crystal clear. 78.2. I'm sorry, there are only 2 examples for this lesson. Here, a point is acted on by a push force and a pull force as shown. All right, again, this is turning into physics, and you know what? That is not our stated purpose here. Okay, that's the picture John gives us. All right. Well, that makes sense, but how are we going to break that into 2 triangles? Well, we're not, because this one isn't a triangle, right? It's just a perfectly flat yank that way, right? And we can see that if you put this on a Cartesian coordinate system, right? This is all right action and no up action, right? So I can just say positive 10 to the right plus 0 to the up. Does that make sense? I don't even need to talk about sine and cosine. I can just look at that and see that my pole is straight across. There's no angle to it. So I'm just going, the point that we get to at the end is going to be 10 and 0, right? 10 and 0. That's so easy, it's hard. Now, okay, so this is part A, if you will. And I got to this really fast without having to use any trig. Now, part B is the other one. And again, we can imagine our whole Cartesian coordinate friend here. 16 is our hypotenuse. Sorry for the messy triangle. 30 degrees is what we've got here. So now we need to do plus some, oh no, I don't know. Well, I do know it's plus and plus because I'm in the first quadrant, right? So it's plus to the right and plus to the up. So plus something to the right, plus something to the up, and then I'll add it to this. Now, how do I find that? Oh yeah, this is what helps me. Adjacent, opposite, hypotenuse. I do have the value for the hypotenuse. And I know that, I'll write them all down again. Sine, cosine, tangent. Oscar had a hold over Arthur in the alley and the scene was not pretty. So when I want to get this right calculation, I want the adjacent side to be what I'm finding, and that means I need cosine. So this one is going to be 16 cosine of 30 degrees. Cosine is always associated with the right value And to shortcut the process, we cross multiply in our heads, right? This would be cosine of 30 degrees equals A over 16, and then we would cross multiply and bring it up. We do it every single time. You don't have to write that out every time. You can just jump to this form. And then the opposite side is going to be equal to 16, same hypotenuse, times the sine of 30 degrees. Sine is always associated with the up value because sine is the opposite, and the opposite measures what we're trying to measure. Okay? So I run these through my calculator, which is a lie because my camera is also my calculator, and so I'm filming. Cosine, this one is 13.86, and 16 times the sine of 30 is 8. Nice and even, right? Okay, beautiful. Now we're ready to add this and this, right? Let me just squiggle those harder so you can see. All right, this is pretty easy. I can add this in my head. So it's going to be plus 23.86 to the right plus 8 up. Okay, these are the rectangular coordinates of the combined force. That's what happens if you pull it straight for 10 units of pulling and then pull it up at a 30-degree angle for another 16 measures of pulling. I don't know what that means. Okay, now this is helpful, but very often in physics, this is not a helpful way to write our answer because we might need to combine it with another force. And so we want to rewrite this as a polar coordinate. So how do we do that? I want to take it from the beginning, right? So plus 23.86 to the right plus 8u, 8 units to the up. We can see by the double plus that this is going to be a first quadrant angle, right? Because it's positive, positive. Remember, the quadrants go 1, 2, 3, 4. This is positive right and positive up. Over here, we've got the negative rights, but still the positive ups. Over here, everybody's in negative land. And then over here, the right is positive, but the ups are negative. This is not anything you need to memorize because it's logic will allow you to recreate that. But if you're struggling a little bit with where's the positives and negatives, there's some help. Okay, so we've got a triangle that is 23.86 on the right axis, and then it's 8 on the up axis. So our point is about here. Okay, now what I can do, I know this is 23.86, and that is my adjacent side, right? Because there's my angle. And this is the up value. Instead of measuring it on the axis, I want to measure it here on my triangle. This is equal to 8, and this I know is the opposite side. Now, in order to write my answer in polar form, I need this information, don't I? This is the hypotenuse, and this is the angle. I don't have either of those pieces of information that I need. So I have to figure out clever ways to get them. All right, well, in order to get the angle, I'm going to use tangent, always. And here's what we remember. Tangent equals over Arthur, right? The tangent of any angle is equal to the opposite side over the adjacent side. Those are the two sides we have. So we can say that the tangent of our angle in our triangle, which we're going to call theta, is equal to the opposite over the adjacent. Oh, 23.86, right? So this is my basic formula. I've got those two sides, so I just fill them in. Now, this is a case where I know the decimal number, or at least I can figure it out, right? This, if I take 8 divided by that, it's going to give me a decimal number. And what I want is the degrees, right? I want that, because that is the number that goes there. These are the two key considerations that tell me I need to use the inverse tangent button. It's the one where you have to hit the second key first, okay? So I'm going to hit second. Well, I'm not going to do that yet, but this is the case where you want to use that second button because we know the decimal and we want the degrees. The other button, the one that you don't push the second to get, the regular tangent function, that's when you know the degrees and you want the decimals. All right, so this is the backwards one, if you will. All right, so what I'm going to do is I'm going to take 8 and I'm going to divide it by 23.86 and I'm going to hit equals. Then I'm going to hit second, inverse tangent, equals, and the answer that I should get right then and there is 18.54. That is the measure of this angle. Now, sometimes, depending on what quadrant you're in, sometimes you have to think a little bit more to figure out what angle belongs here. Sometimes it's not that straightforward. We're lucky right now because we're in the first quadrant, and so this is definitely the number we need, right? Because we measure like this to that line, and that's 18.54 degrees. So we're golden right there. Okay? Depending if your triangle is over here like this, say, then this measure does not tell you what you want. You have to figure out that measure. But we're lucky this time, right? Because the number that goes in your polar vector starts here and measures back. So you have to be careful to make sure that the number you're putting here will send anyone looking at this to the right place. All right, now we need the hypotenuse. Excuse me. There's a couple ways to get that. One involves, okay, to get hypotenuse, you can use trig functions to get that, but most students prefer to use Pythagorean theorem. Okay, and the way we've got side, and we want the third side. Notice the side we're missing is the hypotenuse. So we're going to say 23.86 squared plus 8 squared equals h squared, right? So then to isolate our h, if we take the square root of this, we will get our value. So here's what you have to do. You have to take 23.86, hit the x squared button, add, and this one you can just do in your head, right? 64 equals, then you should get a number that's big, this plus 64. Then you hit the square root sign and you will get h equals 25.17. And that number goes up here. Okay, so we did all of this in order to take our rectangular coordinates and convert them to polar puppies. Once you get the hang of this, it is extremely satisfying and fun. This, by the way, is called the resultant force. Which is a fancy name for the answer. It means the sum of the two answers, right? Remember, we figured it out in rectangular coordinates, and then we converted it back to polar. And again, in physics, that's probably what you would actually want to do. All right. I know I went slow. I know I went in a lot of detail. I'm trying to make sure that this process of taking polars, combining them as rectangulars, and then converting them back to polars. You guys, by now, I really want this to be pretty smooth and pretty straightforward for you, right? It works exactly the same whether we're using polar coordinates or if we're talking about complex numbers. Remember oh no, you didn't do that, never mind. That's the other girls. I said other girls like you guys are girls. Sorry, gents. I hope that Hammy and Jeff do not get profoundly offended. I was thinking of my advanced mathematics ladies who are doing this plus, so get pumped. But I need to make sure that this is super clear in your head. So if it's something you've been struggling with, we'll talk, and I want you to give me feedback on whether this makes sense to you. Yay! That's the lesson, end of lesson 78. I hope you enjoyed it. I hope you will speak to me again. Goodbye.